Hey everyone, it's Colin. How's it going? The processors in our devices have gotten dramatically faster over the past few decades, but the rate of innovation and improvement has slowed down in recent years. This time, let's talk about what makes for a fast CPU and where the future's headed. So this particular episode was suggested by a viewer over on Twitter, and I think it's a really pertinent topic these days because computational power is becoming, in some ways, a bigger and bigger thing, but in other ways, less and less of a big deal. But most importantly, I feel like where CPUs and processors are headed and where we've been in recent years can explain a lot as to what's going on with computers and technology devices in the global marketplace, why people are buying certain things and not others. Of course, the whole business and marketing side of all that is really kind of outside the scope of this topic. I wanted this one to be a bit more technical in nature, but I do find it interesting how a lot of this stuff kind of ties together. One thing that I do want to note is that CPUs and processors and, computational engines are an incredibly deep and complicated topic, and there is no way that I could go into all of the different aspects as to how a CPU works and what the history is and what are all the kind of derivatives and offshoots are in a podcast episode like this. I want to keep this kind of accessible by the vast majority of people who may want to watch or listen to this episode. So I'm going to be speaking at a bit of a high level in general as to how CPUs work and kind of where we've come from, where we are now, and where we're going. So if there's a particular super deep topic that you were hoping I was going to talk about, I'm sorry, but it's such a complicated topic, and there's a lot about CPUs in terms of the actual engineering and physics and science behind them that I don't even know. I don't want to put misinformation or anything out there. But in general, what makes for a fast CPU? Where have we been and where are we now? Of course, we are orders of magnitude faster now than we were in, say, the 1980s. A computer in the 80s, the CPU performance would be measured in, if you were to look at just kind of the specs advertised with the computer, its CPU would be measured in maybe the single digit megahertz, 8 megahertz or 12 megahertz, 16 megahertz, something like that. Pretty small numbers. And now we've got computers and even mobile devices that advertise in the gigahertz, 1,000 times faster or more. And that's just mind-blowing. We're growing leaps and bounds where we are now from where we were just, say, 30 years ago. And there is an interesting thing that I should note about how we define, performance on a processor or on a CPU. A lot of people say, well, that's a really fast CPU. That's a fast computer. That I would say used to be an accurate way to describe a computer that performed well, was fast, because, the real defining way to say one CPU was, more powerful than another was to just look at clock speed, because in general, clock speed was the biggest defining factor as to how much performance a computer had. Nowadays, clock speed is not irrelevant, but way less relevant. So it kind of strikes me funny. People say, well, I've got a fast computer, I've got a fast phone. That term fast refers to clock speed, but clock speed isn't the biggest factor anymore. So let's talk about the factors as to what makes for a so-called fast or well-performing processor. There are really kind of three aspects, as far as I can think of, that make for CPUs that perform well. Of course, clock speed is going to be one of the first ones that comes to mind. And it's basically just a clock. in terms of setting a repeating cadence. What the clock speed in a computer does is it sets the tempo. When CPUs operate, they need to work with all the other components inside the system. And they even need to work with components inside the CPU itself. And so if there wasn't anything that kept a pattern going that said, like a gatekeeper, when certain things could happen, then CPUs would be way less efficient, right? They'd be trying to send data to other parts of the system that may not be ready for it yet, or two devices may be trying to talk to each other at the same time and they'd conflict. All sorts of bad things were happening. So one of the very first things that they engineered with processors is the idea of this clock. And it's basically just this rhythm, this tempo inside the computer that dictates all the stuff that happens on like a pattern. Right? So the idea is you don't speak out of turn, you don't, cut in line, you don't try to talk when somebody else is talking. The CPU and the rest of the parts in the system all kind of work on this pattern, this frequency. You get so many units per second that it can do work. And doing work per unit is another thing that we'll get to in a moment, but it's really just kind of like the base pattern, the base cadence at which a computer operates. So a 3 gigahertz CPU is going to do more cycles than a 2 gigahertz CPU, that sort of thing. But that isn't the only thing that dictates how much work gets done, right? You would think, well, if you're doing so many instructions per clock cycle, just cranking up the clock cycle means you get more instructions, more math done in the CPU in the same amount of time. And to some extent, that's true. And that certainly was more true back in the 80s and 90s with less advanced CPUs than we have now. But we're kind of starting to reach limits in how fast we can push CPUs from a clock speed standpoint. Clock speeds haven't really grown or advanced that much in the last, say, 10 years. I mean, we have 3 gigahertz CPUs now, and there were 3 gigahertz Pentium 4 chips, quite a while ago. So we're not growing by leaps and bounds in terms of clock speed, which is why trying to compare CPUs just by clock speed isn't really a fair comparison anymore, like it may have been decades ago. Another thing that makes for a well-performing processor is core count, and to some extent also socket count. So, obviously you've got this collection of transistors within a CPU, and they all work together to basically crunch numbers and do math, right? Because that's what CPUs do, is they just crunch numbers. And the more transistors you have, the more math you can do in general. Again, I'm speaking in kind of high-level general terms. And the faster you make those transistors work, the more math you can do. So that's the clock speed. But there are kind of limits that we have now as to how many transistors you can pack into a CPU. So the idea is, instead of just always chasing only how to pack more transistors in or make them go faster, what if you just add more CPUs? So probably, I don't know how long it's been, maybe 15 years ago, the early 2000s, maybe mid 2000s, we started to see dual core CPUs. Prior to that, getting more than one core or more than one CPU in a system was really kind of a fringe case. Like, we didn't see it from a consumer perspective. You'd buy a computer in, say, the mid to late 90s, you'd get one CPU and it would have one core. It would have one collection of transistors doing all of that math, and it just was what it was. But starting in the mid 2000s and definitely extending into now, we're getting to a point where they're starting to simply pack effectively multiple CPUs into a computer. And oftentimes they're packaged together. So you get, like if you were building your own computer and you're buying a CPU, it's going to be one physical device, that you put into the motherboard. But within that that device, that piece of silicon, you've got multiple CPU cores, effectively multiple processors, and they're all designed to work together. And this is the concept of scaling out instead of necessarily scaling up. And if you think about it, it's an incredibly efficient way to add more computational power to a computer, right? If you've got limits on how fast you can make a CPU work and how many transistors you can physically pack into a CPU before things start to fall apart, then just add more CPUs. Start putting more processors together and get them to work in parallel to get that math done. Divide up the work, amongst the multiple cores and just get things done faster that way. And we've seen a really big growth in those types of processors since they started being seen in the mainstream. The first ones were like dual core. You'd have 2 cores in one physical chip. And then quad core CPUs started coming around, 4 cores in one chip. And now we're seeing dozens of cores in chips. There are server processors that have 20 or more cores in them. And they are expensive, yes. These are chips at this time in late 2017. A server chip with 20 cores in it costs thousands of dollars, but it still ends up being a really good value in the long run, just in terms of how much you can get done within that single, physical processor chip. So core count and then socket count is kind of the next step. Is if you don't get enough cores in the CPU itself that you want, well, you can scale to multiple separate physical CPUs, right? So most desktops, laptops only have one socket, or place for a physical CPU in it. But a lot of servers come with 2 sockets. You can put 2 separate CPUs in there, and generally they have to match. But there are other server platforms that can have 4 sockets or even more. So it's this just mass scale out. And within that single CPU, by adding multiple cores, you're going way, way beyond what a single core could do from an engineering perspective. Like I said, it's the most effective and efficient way to add computational power to a computer is to throw more just actual full CPUs at it than trying to get the one CPU that's in there to go faster. The biggest part about the struggle in trying to get CPUs to be, better performance and all that, obviously there are form factor limitations, especially with mobile devices, right? We can't keep throwing cores into mobile devices because then you start reaching physical constraints. You don't have that much room for a big, physically big CPU inside something like a smartphone, but you keep wanting more performance. And so that's where kind of the third aspect of what makes for a fast CPU comes into play. And it's this thing called IPC, or instructions per clock. And it's basically how much math can a processor get done for each clock cycle, right? Within that 2 gigahertz or 3 gigahertz or whatever the clock speed is, how much math can get done within every single one of those steps. And so IPC, I would say, is probably the one thing that the industry has been struggling the most to try to advance. It's not easy to crank up clock speed on CPUs, but we have been still seeing some advancement there. For example, the computer that I have right now, it's got an Intel Core i7 7700K. It's a fast CPU. It's a quad-core CPU. It operates at over 4 gigahertz. And that's a number that 15 years ago we didn't have in production CPUs. I don't even think we had production CPUs that fast 10 years ago. To get a CPU to go that fast, you were basically one of those extreme overclocking kind of nerds, where you'd be dumping like liquid nitrogen and stuff just for lulz to try and see how fast you can get a CPU going before it just utterly fails. Nowadays, we've got CPUs that can hit those numbers, but, again, there's limits as to how fast we can get the clock to go. So the big challenge, and where other than core count comes into play. The other big bang for buck is IPC, instructions per clock. How much math can you get a CPU to do per cycle? An easy way to think about these three factors is kind of like a comparison to a car engine. It doesn't match up perfectly, but it's the best example that I can think of. If you think of the clock speed of the CPU, a lot of times that's like the engine RPM, right? You know, do you have the engine revving at 2,000 RPM or 3,000 RPM or 4,000? You know, how much horsepower does the engine make at those different speeds? And yeah, we've been able to kind of get CPUs to go faster in that regard over the years, but there are still limits, right? You know, we've been able to get production engines to go a little bit faster over time, but there are still limits as to how practically fast you can get them to go. In terms of core count, well, with a comparison to like an engine, that would be like how many cylinders you have, right? A single core CPU would be like a 1-cylinder engine. A dual core would be like a 2-cylinder. And obviously, the more cylinders you have in an engine, the more likely you are to make much more horsepower out of it, more power output, even at the same engine RPM, right? So a dual core CPU, not exactly twice as much, but you're going to get significantly more performance out of a 2 gigahertz dual core CPU than you would out of a 2 gigahertz single core CPU, right? You get it. The third thing, the IPC, that's kind of like how much power each cylinder can produce, like what that cylinder's displacement is, what its compression ratio is, just how much horsepower per power stroke each cylinder can make, how much torque it can make. And like I said, that's one of the trickier things for the computer processor industry to try and advance. And in some ways, that's a tricky thing for engine manufacturers to advance too, is trying to get more power out of the same number of cylinders running at the same speed. But IPC does continue to go up every year or two, though not nearly as fast as what we've been accustomed to in years and decades past. IPC depends on a lot of things, but perhaps the most interesting thing to talk about when it comes to IPC is what they call the process, or the process size. Right, computers are made up of all these teeny tiny little transistors, and they get packed into this certain footprint. And the process size basically defines, how big each of those little transistors is. And so the smaller you can make each one of those, the more you can fit, and therefore the more work you can get done. And right now in late 2017, we are looking at 10 nanometers as being kind of the typical process size for the current crop of CPUs. And I should note that in the late 70s and early 80s, process size was measured in micrometers, which is a unit of measure larger than nanometers. Nanometers, order of magnitude smaller than micrometers. So just as frequency speed has kind of taken that same leap, process size has taken that same leap. We're just dramatically smaller now than we were decades ago. And that's a good thing. Smaller means faster, I should say, more powerful. So right now, 2017, we're looking at 10 nanometers as being kind of, the current crop of high-performing CPUs, even mobile CPUs like in smartphones and tablets are getting onto that process size. It takes us a while to get to every new step in process size, right? Because it just gets harder and harder to shrink these things down. In 2018, the hope is that we'll reach 7 nanometers, although that's still in kind of the testing and prototyping phase. We'll see whether we actually can get there or not. But Hopefully we'll get to 7 nanometers in 2018, and that'll yield a pretty decent jump in CPU performance. And then the other hope is that 5 nanometers will come by the year 2020. And that's maybe a bit more optimistic of a goal than 7 nanometers in 2018. We'll again have to see where that goes. But that's really kind of the roadmap for CPUs going forward, right? Is trying to continue to advance IPC, instructions per clock, because the frequency thing, we're kind of running out of runway there, I feel. And core count's definitely the cheap and easy way to do it. And we've been seeing CPUs of all varieties adopting more cores. Even mobile CPUs and smartphones are dual core, quad core, even 6 core. Apple's latest iPhones, iPhone 8 and iPhone 10, those are literally 6 core CPUs. There's like 4 slower cores and 2 faster cores, and they can turn them on and off and use them as necessary based on what kind of demand there is for computational power versus what kind of power consumption they want to use. If it's not that urgent of a thing, maybe they throw that task at one of those lower power cores that help save your battery life. So IPC is really kind of the major frontier, I feel, where we hopefully will start to see some more breakthroughs. That's shrinking the process size even further down, but it's by far the biggest struggle, I feel, for CPU manufacturers. There are a few other factors as to what make for fast CPUs, and then also, where CPUs are going. It's kind of outside the scope of this episode, but the actual architecture of the CPU plays a pretty big part. We're used to, in our desktops and laptops, something called CISC, or Complex Instruction Set Computing CPUs. And those really kind of harken back to, the 70s and 80s, when the amount of storage and RAM was very limited, right? In a nutshell, the computer design back then said, we've got limited amounts of RAM and storage, so let's try to write the programs in such a way that minimize their footprint in that regard, though they may be a bit harder or more complex for the CPU to actually execute those tasks. So the CPUs basically have more things that they can be doing. They've got more options on the menu in terms of the types of computational processes they can do in these CISC CPUs. The downside is that it hurts efficiency. So the alternative type of CPU is what they call RISC, Reduced Instruction Set Computing. And they're not new. They've been around for decades as well, but it takes a different type of computer architecture and different type of programming to take advantage of CPUs like that. But they do offer a good performance advantage because they've got fewer types of computations they can perform, but they're much more efficient at performing the ones that they still do, right? It's a narrower menu of things they can do. Think of it this way. You've got a cook in a kitchen. What's more effective or more efficient for that cook to be doing? Just cranking out a whole bunch of hamburgers and hot dogs, or working off of a full menu? And in addition to hamburgers and hot dogs, they also simultaneously have to cook pizza and spaghetti and macaroni and cheese and a bunch of other stuff. I mean, yeah, this is a very high level way of describing it, comparing CPUs to food, but that's kind of the idea, right? If you can reduce the variety of types of calculations a CPU can perform, it can be made more efficient at performing the ones you still want it to perform. And you leave it up to the software to figure out how to use what's on that menu to get done what it wants to get done. Like I said, RISC CPUs are not new, but we've actually been seeing a major growth in RISC computing in the last, maybe 10, 15 years. And it comes from a place you wouldn't expect. It's not in our desktops and laptops. Those predominantly still run x86 type CPUs, from Intel and AMD. RISC computing is in a place you wouldn't recognize or immediately think of. It's in here. Smartphone and tablet processors are predominantly based on ARM CPUs. ARM is using the RISC type of model for designing processors. So our smartphones and our tablets are ultra efficient and have gotten to the level of performance that they're at, partially because of really good process size and core counts and all that, but also because they're RISC type processors instead of CISC. I mean, I've been seeing benchmarks that have shown the latest crop of smartphones are as fast as like pretty decent mid-level laptops, which is a little bit mind-blowing considering how much better battery life you get out of a smartphone or a tablet compared to a laptop. CPU architecture and then the software that runs on top of it has a really big thing to do with how well your CPU performs. So where are things going from here? Well, obviously, core count is going to be the biggest, cheapest, easiest way to get more performance out of processors going forward, I feel. We've already seen this proliferation of core counts. Obviously, the scale out model is working way better than trying to scale up. So we're going to continue to see that. We're going to continue to see not only our mobile devices, but our own computers at home and servers as well start to really get into multi-processing, right? Where we've just got that load distributed amongst a whole bunch of logical or physical processors to get all the work done in parallel. The other thing that I think is going to be really big going forward is, like I said, that architecture. We're going to continue to see this proliferation of RISC computing. It's really just a matter of trying to get the consumer market there for more types of computing functions. I mean, obviously we're there for smartphones and tablets. We don't really have much in terms of laptops and desktops that run RISC CPUs. Now, Microsoft has actually been starting to dabble in this. Some of those Surface tablets ran ARM-based CPUs, and Microsoft, ported versions of Windows 8 and 10 to ARM-based CPUs. They kind of backed off on that for a little while, but it seems like they may be getting into it again. So there's a big future there. It's just a matter of getting the OSs to make the leap, and then of course the software to make the leap, because the software, all the programs and everything you run on a computer have to be rewritten to work properly on that different architecture of CPU. Otherwise, you've got to go through like a translation layer to interpret that code and emulate it basically, from CISC to RISC, and that's always going to rob you of performance. So that architecture is the other big thing. I think that's going to make a major impact on continuing to improve CPU performance going forward. Of course, process size, like we talked about, going from 10 nanometers to 7 to 5 is going to yield some pretty big incremental gains. But the predominant thing is we've really broken Moore's Law. Moore's Law is one of the founders of Intel, and it's not really a law because it was never totally proven, but it's a saying that goes, the number of transistors in a CPU will double every 2 years. You could loosely translate that as saying CPUs are going to be twice as fast every 2 years. For a long time, that actually really held true through the 80s, the 90s, and the early 2000s. I remember days when a 3-year-old computer was noticeably slower, right? It was a really big deal. Getting a new computer, every time you bought a new computer in like the 90s and going into the 2000s, you could really feel that performance difference. It was a big thing. You felt like you were really getting your money's worth. But, in the last 6-7 years, that hasn't really necessarily been the case, regardless of whether you're looking at a desktop or a laptop or even a mobile device. I mean, there are people that are still rocking 6-7-year-old computers or 3-4-5-year-old smartphones, and they're getting by just fine. And that's because the industry hasn't necessarily hit a brick wall in terms of advancing performance, but it's certainly found new challenges. We're getting to a point where trying to make CPUs faster is just getting harder and harder. And because we've been seeing slower increments, people haven't just been as interested in upgrading. But anyway, like I said, this was going to be just kind of a really rough overview of my thoughts on where CPUs are and are going. If you know more about these, if there's an aspect that I missed, please feel free to shout that out down in the comments below. I want to hear from you. I'm also curious, have you been thinking about upgrading your computer lately or your mobile device? Is performance as big of a deal for you now as it maybe was quite a while ago? Have you purposely been holding off on upgrading your device to something newer just because you knew the new one wouldn't really be all that much faster? Something like that. So again, also let's keep that conversation going down in the comments. Also, quick little note, if you're interested in MP3 versions of these podcasts, so you don't have to watch them on YouTube, I'm happy to oblige. They're all available over on my Patreon page, as little as $1 a month. Gets you access to it. I'm not saying you need to do it. I'm happy to have you continue to watch me here on YouTube, but if the MP3 thing is interesting to you, I invite you to maybe check out the Patreon page. Try to help support the channel. I really appreciate it. So, if you like this episode, I would appreciate a thumbs up. Be sure to subscribe if you haven't already. You can follow me on Twitter and Instagram at thisdoesnotcomp. And as always, thanks for watching.